So what I want to do here is that I want to go share my screen and sort of review what we did last time. And one of the things that we said is that after the discovery of the positron, that is the anti-electron, they were hunting for the proton. And one of the things that they found here is that they found a reaction that would be able to sort of like make quick work of it. So they took a proton, they accelerated it, they hit another proton.
Successfully.
And this was in a vat of liquid hydrogen. By the way, that's exactly what CERN does today. CERN used to accelerate electrons and positrons. And there's a good reason why you would want to accelerate electrons and positrons, because the reactions are cleaner. Proton interactions are very messy because you got to deal with the 3 quarks and the gluons inside of it. And so it causes it's just really hard to deal with it. There's a lot of residue that comes out. So once you hit that one proton, they were saying that I could take these 2 protons, I could produce 4 protons with one of them being an antiproton. And so typically the question is, what is the minimum kinetic energy? And remember, kinetic energy is what we call PC. So what is the minimum required kinetic energy in order to make this reaction occur? And so what we did here is that beforehand, we imagined that we have 2 particles, one at rest, one coming in with certain momentum and kinetic energy. And then after the collision, we have 4 particles going out. And so the thing that was done at that time is that they used this invariant mass of the system. And so you have the lab frame and you have the center of mass frame.
Crawler blurred.
And so one of the things that you want to do here is that you want to go in and you essentially want to choose the most difficult one to be the center of mass, and you choose the easier one to be the lab frame. So with that means we have choices. We could either say before the interaction, being P1 and P2, or after the interaction, which is 3, 4, 5, and 6. Since this is way too complicated, you can't solve a 4-body problem. You just can't. Impossible. And so you can do this trick where you pick this to be the lab frame. So in essence, you come in here and you just say, okay, that's too complicated. This one's too easy. So this is the easiest for 4-particle collision, and we can handle 2-particle collision. I mean, we do that in 4A. And so then, here we go. This has momentum and energy. This only has rest energy. Then all of these guys have momentums, but in the center of mass frame, all of these momentums go to 0, and now you only have rest energy. So then what we did here is that we went in and we started doing the calculations. I write down the invariant for P1 and P2. So I get this. I know that that guy's at rest, so I only get P1 here. And then when I look at the center of mass frame, all of these momentums go to 0. And so all of these energies are all the rest energies. So then mathematically, that's just fairly easy here. So what you're seeing here is that each of these energies is the 4 energy when I'm talking about E1. And when I look at E2, that's only the rest energy. So what I did here is instead of writing mc squared, I just kept that as E2. Why? It's just easier to write E2 than mc squared. That's the only reason. So I wrote this all out, and then I have minus P1 squared c squared. And then over here, I have 4 of the rest energies because antiparticles and regular matter particles have the same mass. So then I come in here and I'm going to solve for the total energy of the proton, E1, because I know that E1 has that PC value in here. So then what happens then is that then I just go in and I continue the algebra. So I write out E1 squared, and then you could see here is that this guy right here is E1 squared. And then here's E2 squared. And then this is the cross term. Okay. And then you could see here is that the notation that I use is that if I have the same term, then I use the same color, and I only draw one line. And then I go to the next one. And then you could see that these two terms are the same. So you could see that I go in and I draw, in this case, I used the green and I did two lines. So typically, if I had a long calculation, one of the things that I would do then is that I would start with my red. Like, for example, when I was a graduate student, I had a 5,000 term integrand. So what do? You learn to become very creative in how you go back and check this shit. So I would have my red pen, I'd go 1, then I'd go 2, and I would do that all on subscripts. And then on certain ones, I'd go superscripts and I'd put them up on top. And then I would use different colors. So then it's easy to follow it. So now you could see here that the reds here, single underline, they cancel out. And then these guys add. But remember, here I have E1, but E1 is P1 squared plus M squared C to the fourth square root. So I still have to deal with that. And so what happens then, what I'm going to do then is that the next thing I'm going to do is that I'm going to move everything to the right. Okay. So if I do that, I'm now going to solve for E1. So then I'm going to get E1. And in this case, I'm going to get 4mc squared squared. Then I get this term right here, which will be minus 2m squared c to the fourth. And then I got to divide this whole thing by 2mc squared. Now, if you're looking at this thing, note that this guy's 16. This guy is 2. So I get 16 minus 2, which is 14. And then look at this 2 here. So I get 14 divided by 2. That's going to give me 7. So this guy should be 7m squared c to the fourth. But I know that this guy is going to be what? P squared c squared 1 plus m squared c fourth square root. So ultimately, we don't care about the rest mass. We're interested in P1C. So now what I want to go do here, I need to come in here and I need to, for P1C. So if I do that, I got to square everything. Okay, so if I square everything, I'm going to get P1 squared C squared plus M squared C to the fourth. Wait. I have wrong units somehow. Why are my units wrong?
Hey, Carlos,
Yeah.
I think you might have forgotten the denominator on E1.
Oh, thanks, Josh. I needed that help. Man,
Yeah,
you're
it's
the
all
man.
good. Thank you.
Yeah, this guy's, I forgot to write MC squared here.
Oh, Josh.
Yeah, so then this should be 7MC squared, and then this will be squared. So then this tells me here that then I'm going to get P1C, and if I bring this to the other side, so note this is 49, this is 1. So then I should get 48 m squared c to the fourth square root. So in the end, what kinetic energy do I need? The square root of 48 mc squared. And then that's what my kinetic energy is right there. So what this means here this is the kinetic energy required of the accelerator to create the antiproton. And that's exactly what was done. So they made sure that the accelerator could create that kinetic energy, and that's what you had here. Here, I gotta go get one thing, and then we'll get started here. Uh-oh, I hope I didn't delete it. I want to do that last example. And I think that this last example is example 2.5. Man, I'm not, here, let me look again. Here, I gotta go get it. I thought I had it, my bad. So let me get a copy to put into which one am I doing here? I'm doing the okay. Sorry for my delay. So here, what you find here is it says find the minimum energy a gamma ray must have to initiate the reaction. You know, gamma ray plus proton going to a pion plus a proton if the target proton is at rest. So when I look at this picture here, let's draw this scenario out. What you're seeing here is that you're seeing this thing. You're seeing, so you're shooting gamma rays. And typically I like to label them with 1s and 2s and 3s. And then again, you have that tank, right? You have some tank that contains hydrogen. And they get the protons from the hydrogen. They don't have a collection of protons. They have a collection, they have liquid hydrogen. And what you'll find here is that this is the guy that we're going to focus on. So I'm going to call this my P2. So then afterwards, what we know is that from this single interaction, right, with this guy right here, this single interaction says that I'm going to get a, coming out of it, I'm going to get a, I'm going to get a pion, and I'm going to get a proton. So a lot of the times what I do here is that I think about this in terms of numbers, and I kind of just label them like this here. Now, I don't know how that pion and proton are coming, but we do know that when I look at the 4 energy of these guys, that if I'm in the center of mass, I have to use a center of mass. So because no information is given about the momentums of the pion and proton 3, the center of mass frame is crucial here, or critical to use. because you can't solve this problem. So it's super critical that you use a center of mass frame. So then, if that's the case, then I could then come in then, and I could say the following thing. I know that I'm going to have some photon momentum coming in, and it has this energy is related to that momentum. When I look at the proton, it has a zero momentum, but its rest energy is the mass of the proton. And then what you're finding here is that the pion, it does have, right? The pion does have momentum not equal to zero. It does have energy not equal to zero. We may not know the details of it. And I know that this third proton has momentum and energy that are not equal to zero. So the issue is, like we've already said before, is that because there's no information about the momentums of the pion and the proton, this is an unsolvable problem unless you use the S invariant. So then I then choose the invariant S squared to solve for P gamma 1, which I'm now going to start writing as P1. So when I'm looking at this, I could see then that in the lab frame, I'm going to pick P1 plus P2, and in the center of mass frame, I'm going to pick the one that has the most uncertainty, which I'll call P3 and P4, right, where P4 is the momentum of the pion here. And so then I'm just going to go and look at this thing here. So you could see here is that in the center of mass frame, I'm then going to write the following thing. I have the energy 1, energy 2 squared minus P1, P2 squared C squared and then I do the same thing for the other case. But in the center of mass frame, as we already talked, this guy is 0. And these guys are the rest mass. So if this is the rest mass, this means that it has to be the mass of the proton plus the mass of the pion squared C to the 4th. Okay, and then if I look at this other side, what we see here is that because this proton's at rest, then we know that I could then come in and write this as E1 plus MPC squared minus P1 C1. And of course, this whole thing is squared. So then what I'm going to do then is that I'm just going to start to square everything out. So if I do that, what am I going to get? Well, the first thing here is that I know that P1's contained in this E1. So if I square the whole thing, I'm going to get E1 squared plus MP squared C to the 4th plus 2 MP squared. Nope. That should be 2 MP C squared times E1. And then I get minus P1 squared C squared, and that's going to be equal to MP plus M pi squared C to the 4th. So let me make sure I did my algebra right here. Okay, so then I'm going to replace this with the 4 energy here. So if I replace that with the 4 energy, I'm going to get P1 squared C squared plus MP squared C to the, nope, this is a photon. I made a mistake here in my thinking. E1 is P1 times C. Because if I look at this, we know that photons have zero mass. I kept thinking that was a pine in my head. So we know that E1 is the same as P1, which implies here that E1 is equal to P1C. So if I look at these guys, look what I'm going to write then. I'm going to rewrite this, then this is going to give me P1 squared C squared. Then I'm going to get MP squared C to the fourth plus 2MP C times P1C minus P1 squared C squared. And then this will give me my mass term on the right. So right away, you could see here is that this guy and this guy automatically cancel out. And then I can isolate P1 now. So now I'm going to isolate. So if I take this to the other side, and then I'm going to divide that by that, I'm going to get that P1C is then going to be MP and pi squared C to the fourth minus MP C squared squared divided by 2MP C squared. Now, I could calculate it this way, but note that if you square out this term, okay, make sure I get my algebra. Is my algebra right? It looks like it is. So then if I start putting in my numbers for this, I mean, then I'm going to get what? Then what I'm seeing here is that I know that MPC is 938 MeV. I know that M pi C squared is 140 MeV. So then I just start plugging in my numbers here. So look at this number. If I bring in the C into this thing here, damn, man, I'm always messing up on the C's. So, the way I factored out the C is not correct right here. Unit-wise, it's not right. What I should have...
C is 1?
What I should have done is I should have written MP C squared, M pi C squared squared. So this is not the same as that. So it's really, this should have been a squared term if I wanted to keep it there. So I'm going to come back and I'm going to say, I'm not going to use that way. That this is the correct term all the way down here. So that the correct term is really MP C squared, M pi C squared squared. So I messed up on my C squared term here. So then if I put this together, I'm now going to have what? 938 plus 140 squared minus 938 squared divided by 2 times 938. And this will give me units of MVC. So if I compute that, my calculator says this is 150 MeV for P1C, which is the same as P of the photon. So I get that. So assuming that my calculator is right, That's what I'm getting. I'm sure we could reduce this algebraically, but I think I'm not gonna reduce it anymore. So that concludes this chapter. So let's talk about the exam briefly. Okay. So when I think about so you're gonna have quiz number 2, and you're gonna have problem set number 2. When is the due date? I don't remember when the due date is.
Halloween.
Halloween. Okay. Now note that there's that due date is really being set so that you can. I mean, it's open longer. I really don't want you to have too much stuff going on simultaneously. So it's not like a hard date, but I'm trying to keep you track here. So when I go and I look at this thing here, here, let me see if I can show you what I'm showing. I'm trying to share my screen with you right now. And when you look at this, my screen here, where are we at? So you're seeing here that the quiz is set for the 31st, but it's open longer. Then the exam I'm setting for the 7th. Now note, it says 62, and that's because I'm kind of messing around with that. But it'll be 100 points, and this is what I really want to talk about. So so this problem set should be the exact same dates, which they are. So if I go back to my screen, what am I really thinking of? I'm thinking something like this here. So this is October 31st for both of them. Then we have exam number 1, which will be, I think it's due November 7th here. But I encourage you to keep going, to try to do it faster. So you're going to see that there's going to be 5 problems, each worth 20 points. So you're going to find 2 problems from the first chapter. So here you're going to get chapter 1, which means that you'll have some type of time, length, contraction, space-time diagram. And then when I'm looking at this problem here, you could see that what we really spent most of our time on was conservation of momentum and energy type problem. I mean, could you do this with the S invariant? Yeah, but remember, it could cost you more though. So you got to be really careful, because we're not looking for threshold energies. That's really one of the problems. And then, oh, no. That's not what God, I think I'm stuck in physics 4A. So you're going to get 2 problems from chapter 1, 2 problems from chapter 2. And so when you look at how I set that up, you're going to see that you're going to get 2 problems from chapter 2. So let me move this down here. And so when you're looking at this thing, you're going to have most likely so you're going to get 2 problems, and they're going to be somewhat similar to the you know, like maybe similar to like one of the quiz problems or one of the straight up, time dilation, length contraction, and being able to see from both frames. So it's going to be super important that you be able to boost into 2 frames. That means you're either going to boost from the S frame to the prime frame or the prime frame to the S frame. And I'm pretty sure one of the problems is already written and it's exactly like that. So you have to see from both frames simultaneously. And I do not expect you to draw on the same space-time diagram both frames simultaneously. I think that could get really tricky. And do you gain a lot more physics by doing it that way? I don't think so. I think you gain some, but not that much. And so when you're going and you're looking at these other problems here, you're going to see that most likely, to keep stressing the same thing, you're going to get these 2 problems right here. You're going to get 2 problems where I'm going to make you use conservation of energy and conservation of momentum. No choice in the matter. If you try to use the S squared, it's gonna cost you so much that hopefully you figure it out and you back out. And then I'm gonna ask you to use the S square invariant, because it's all about using that for energy, right? So you should expect a combination of massless and massive particles. So, and then what you're going to find here is then there's going to be one question on conceptual questions. And typically what I'll do here is that I'm going to try to give you, you're going to have one problem that you'll have 4 choices, but must answer 3 of them. Okay, you'll have 4 choices, but you get to pick the 3 that you want to do. And then it's super important that when you use these conceptual questions, you want to minimize the mathematics that you use. It's really about the concepts, not the mathematics. And I will downgrade you if you try to, if you use only mathematics, I'm going to downgrade you big time. Concepts, you'll see, is going to say use sentences to describe physics concept. And some of you are going to try to use non-physics concepts to try to answer these things. You got to be kidding me. This is a physics course. What the hell do you mean that you're going to try to use everyday language to answer some of these things? That's crazy. So you got to remember that. Okay. And I believe I have a practice exam already set up there for you. So what we want to do then is that we want to be able to, set you up so that you can practice that, look at your homework, and then I'll have regular office hours. And if those times don't work for you, you should then, send me an email and let's see if we can hook up and answer some of your questions.